Hey, so now that we are fully set up, we can be able to answer why doesn't the moon fall to the Earth, right? And in my opinion, this is one of the biggest, the most impressive discovery in early days of the history of physics. It was the first time someone can actually unify a terrestrial phenomena with extraterrestrial phenomena. Well, that's exactly what Newton did. So it is still not obvious, right? Because we've spent a couple of minutes talking about any mass will attract any mass. So there's Earth, there's the moon, so it will attract this down. So what is the force on this guy? Well, one incorrect reason of why it is why it doesn't fall. You might say, well, we just learned about the force sort of depends on the height, right? The distance away, and this is very, very far. So maybe it's a very small force. However, yes, this distance is very small, right? Sorry, this distance is very large over here. However, the mass of the moon is also pretty significant. It's not like an apple, it's a lot of apples, right? So it will actually create quite a significant force. Now, that's still not the reason, because even if this is a very small number, which it is pretty small, but over time, this is the only force pulling it down, then over time, it will crash into the Earth. So because you don't have a string that is holding it to the ceiling, you don't have a pillar that's stopping it. So that is not the smallness or largeness or whatever the value of that number is. It's not the reason why it's not crashing to the Earth. So what was the traditional theory of that? Well, before Newton have figured this out, the traditional theory is clearly the incorrect one. But what was that? Just to give you an idea, right? There is the Earth. And people say, hey, we have a theory of gravity is that everything drags towards the Earth, right? So if the apple over here, if there's an apple over here, since the early days in the Greeks, everyone knows the Earth is round. That's fine. We will just have a theory where sort of all the apples and all the people, everything is dragged towards the center of the Earth. That's fine. We can live with that. Now, there remains an open question of, well, how about the moon? That seems like an outlier. Why doesn't that fall into the ground? So the theory was, well, there is what's called a celestial sphere. It's this magical crystal sphere around the Earth, and it's like a marble that's gonna move along the sphere. Don't ask me what the sphere is. What is it made of? Is it crystals or whatever? It's just there is a difference between the heavens and Earth. That's the way they put it, right? Things on Earth follow one set of law. Things on outside follow another set of law. Now there is the sun as well, and the Earth is basically this whole system moves around, right? The Earth will move around the sphere. So the sun has a sphere, has this celestial sphere as well. So it's a celestial sphere. And this system, right, the moon will move around a sphere around the Earth will move around the celestial sphere of the sun. And how about the distant stars? And then there's a huge sort of sphere around everything, and that's where all the stars lie. Okay, so there may be a lot of stars here, a few stars here, a few stars there, and right, so all these are distant stars. So there's a huge sort of dome around everything, and this is the universe, right? This is the solar system, this is the universe. So their theory, this is the traditional Greeks came up with this theory, right? And if you look at all the great Greek philosophers of the book, and you'll see a lot of these spheres going around. Now, to give them credit, some of the things are not too wrong. The moon does go around in an orbit like this, and nowadays we call that an orbit because there is no sphere. The orbit just describes the path that it goes. So it does goes in roughly a circle. The sun does goes around a circle. That part's right. Part that's wrong is all the stars do not lie on the same plane. They do not lie on the same sphere. There are some that is far, some that are close. These are basically just all scattered throughout the universe. And the fact that stars are just like the sun is just one of those stars is another big discovery in astronomy. But I can sort of forgive that, right? Back then, you don't have powerful telescopes. I can forgive the fact that you think all the stars is over there, but what cannot be forgiven is you are having two sets of laws. There's a law that is sort of the terrestrial law, right? Everything is grounded, and you have an extraterrestrial law, something that is away from the ground, and it follows a separate set of physics. Now, the great genius of Newton is realized this is all just nonsense, and what he thought is this: if the apple, well, legend says that he thought about this when an apple hits his head. But that's probably not true. More realistically, it's probably he saw an apple fall from the tree and he realized, hey, the gravity of Earth is pulling the apple even though nothing is touching it. Well, what is stopping it from pulling the moon? Well, it must act on, so the weight, sort of, it's a bit weird to call that force the weight, but it's called, yeah, it's a force of gravity, right? It must act, if it acts on an apple, it must act on the moon as well. Okay. Now he needs to solve. So he first rejected the idea there is a separate law. There is just one law, he believed, and it's a universal law of gravity. Now he needs to set out and answer the biggest question that everyone asks. Why doesn't it fall? And this is his big discovery. Imagine you go on top of a mountain and you have a cannon, right? And you shoot a cannonball horizontally with some initial velocity. Let's say, what will happen? Right? You shoot some velocity, or it follows a projectile motion. We understand, well, it will just fall somewhere like this. What if you shoot it with a larger velocity? Larger initial velocity? Well, it will probably go a little bit further down here, sort of follow a parabola. Why is because at every single point, right? At every single point of the cannonball, the force is pulling it to the ground, to the center of Earth. Now, if you shoot it even harder, it'll go here. We shoot it with a really, really big initial velocity, then this would sort of, go as far as it can. Now, if you shoot it really, really hard, right, with a really large horizontal velocity, there is attraction of gravity at every single point towards the center. I think you see where this is going, right? There's a force that is constantly towards the center, right, perpendicular to the velocity. It is, right, the force that is, what is that called? Well, that's a centripetal force, right? And if you do that, first of all, it will go all the way and maybe fall just before here. But if you can really make that large enough, there's a critical point where it will go all the way and hit you back in your behind. So the first thing you must do is duck. And if you are able to duck, sort of move out of the way, then this thing will just go on forever and ever like this and keep going in and what's now called an orbit. So this, in the moment, you can actually see this very famous picture in Newton's book. And I think that is one of the most impressive feat of imagination that he was able to understand. This is what the moon is doing. The moon was probably, there was some initial, we'll figure out where does the initial velocity come from. That's a separate problem, but let's say it has. Then it explains why it never falls. Or another way of saying that is it's always falling. It is constantly, the moon is constantly, if it's here, there's a force pulling it to the center of the Earth. If it's here, the moon, right, as it moves, it has a force pulling it to the center of the Earth. It is constantly falling. It's just the fact that it has a tangential velocity. It has a tangent velocity, right? So as it moves forwards, it falls a little bit. As it falls forward, it also moves forward, right? Because this is a centripetal force. The centripetal force or the centripetal acceleration cannot slow this down. If it cannot slow this down, it will constantly move in the same speed this way. Okay. I will address the fact that, of course, if you shoot it with a larger velocity, you will sort of shoot it out of the way. Right? If you shoot something, it will not go in orbit. So there's a critical velocity that makes it goes into a circular orbit. And this is sometimes called the escape velocity. So if you do that, you'll be able to escape the Earth's gravity. And if you want to go to Mars, this is part of rocket science. You need to achieve this. You need to go beyond the critical velocity into be able to go past and into an escape velocity. So you won't fall back into Earth. You can actually move forward with your life and go to a different planet. So the one perspective is it's not falling, it's just going in circles, and the gravity is providing that centripetal force that's keeping it in a circle. Another perspective, it's always falling. It's just falling at different places, and it's just falling at just in the right different place where it keeps going. Okay, and since there's no air resistance, nothing's going to slow down. If there's an air resistance, there's an extra force, there's a friction pulling down, and it will slow down the velocity. But that's fine. There isn't any. So as a result, the moon will go on forever and ever. And that's exactly the same reason why the Earth goes around the sun. Right? And there is a force of gravity on that. The moon will go around the Earth. Technically, the moon will be attracted with the sun as well. However, the force is so much smaller. The math, because if you look at the gravity, if I put the sun over here, right? The astronomer's symbol is that, compared to the Earth, like that's the force, and that's the distance between here. And if that's the force on the moon between the sun and the Earth. The moon would be between the moon and the sun. You will have that, and that distance is that distance. Let's say it's the same. Technically, we shouldn't share the same variable, but it's close enough. But that is so much smaller than this, right? And as a result, probably less than 1/10 of it. So that effect, or the sun's effect on the moon is much less than the sun's effect on the Earth. So we can kind of forget the sun's effect on the moon, just worry about this. And that is itself another circular motion. So in this perspective, the Earth is constantly falling. It's constantly falling towards the sun. And also just to share with you, if you have never seen this before, this is the Principia Mathematica of natural philosophy written by Isaac Newton. And this is basically where he summarized all his laws of physics and mathematics, where he invented calculus. And one of the greatest books on physics will sort of kickstart the modern physics. And in his volume 3, page 6, it's also written in Latin. So that you will actually see him draw exactly this diagram of thinking about shooting a cannonball and explaining how this is related to the universal gravity theory that he came up with, and how it explains even though you have a universal gravitational attraction, you can keep the moon in orbit. So absolutely a very impressive feat of imagination, and obviously a great leap in science as well.